Picture this. You're an astronomer scanning the night sky, looking for the usual suspects, asteroids, comets, the familiar debris of our solar neighborhood. Then suddenly, your instruments detect something that shouldn't exist. Something that breaks every rule you know about how objects move through space. This is exactly what happened on October 19th, 2017, when Dr. Robert Weiss and his team at the University of Hawaii's Pan-STARRS telescope made a discovery that would shake the astronomical community to its core. They found an object unlike anything we'd ever seen before, a visitor from beyond our solar system. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, and perhaps that name was more prophetic than they realized at first glance. Oumuamua seemed unremarkable, just another space rock tumbling through the void. But as the data started pouring in, astronomers realized they were looking at something unprecedented. This wasn't just any asteroid. This was the first confirmed interstellar object ever detected passing through our solar system. Think about what that means for a moment. In all of human history, every single object we'd ever observed, every asteroid, every comet, every piece of space debris had originated right here in our cosmic backyard. They were all family, born from the same primordial disk that formed our sun and planets 4.6 billion years ago. But Oumuamua, it was a true alien, a wanderer from the depths of interstellar space, carrying secrets from star systems light years away. The first thing that struck researchers was its shape. Most asteroids are roughly spherical, maybe a bit lumpy or elongated. Oumuamua was different, dramatically different. The way it reflected sunlight as it tumbled revealed an object stretched out like a cosmic cigar, with a length to width ratio of at least 10 to 1. Imagine a football field. Now stretch it to be 10 times longer while keeping the same width. That's the kind of proportions we're talking about. In our solar system, nothing natural comes close to this extreme shape. As Oumuamua tumbled end over end, completing a full rotation every 7.3 hours. It painted a picture of an object unlike anything in our cosmic experience. Its surface appeared reddish, the color of ancient metal exposed to eons of cosmic radiation. This hue told a story of unimaginable journeys through the galaxy. Dr. Weiss found himself staring at data that challenged everything he thought he knew about interstellar objects. We've never seen anything like this in our solar system, he told his colleagues. And the weight of that statement was staggering. The trajectory analysis told an incredible story. Oumuamua had approached our solar system from the direction of the constellation Lyra, but its path suggested it hadn't originated from any specific star in that region. Instead, it appeared to have been wandering through interstellar space for who knows how long. A cosmic refugee with no clear home. But even as the excitement built, subtle warning signs began to emerge in the data. Signs that would soon transform this remarkable discovery into one of the most controversial and puzzling mysteries in modern astronomy. As telescopes around the world continued tracking Oumuamua through the autumn of 2017, Astronomers expected to see familiar patterns. After all, we've been studying comets and asteroids for centuries. We knew how these objects were supposed to behave. We were wrong. The first anomaly was subtle but significant. When comets approach the sun, they develop what astronomers call a coma, a glowing envelope of gas and dust that gets heated and blown off the surface by solar radiation. It's one of the most reliable signatures we know. Oumuamua showed no coma whatsoever, despite showing no signs of comet-like activity. Oumuamua was accelerating away from the sun faster than gravity alone could account for. This shouldn't happen with an inert asteroid. When objects accelerate in ways that gravity can't explain, it's usually because they're outgassing, ejecting material that provides thrust. But Oumuamua showed no signs of OUTGASSING, Dr. Marco Micheli from the European Space Agency, who led the trajectory analysis, found himself facing a puzzle that kept him awake at night. The acceleration was small but definitely real, he explains. Tiny by everyday standards, but huge in terms of what we expect from an inert object. Then came the light curve data, and with it, even more questions. As Oumuamua tumbled through space, the amount of sunlight it reflected varied dramatically, much more than any normal asteroid. The brightness changes suggested either an extremely elongated shape, as we initially thought, or possibly something even stranger, a flat, pancake-like object tumbling end over end. Some models suggested the object might be less than 100 meters thick while stretching over 800 meters long. Both scenarios were virtually unprecedented in nature. Desperate to find conventional explanations, astronomers proposed increasingly creative theories. Maybe Oumuamua was made of solid nitrogen, like the surface of Pluto. Maybe it was composed of hydrogen ice, creating nearly invisible outgassing. Maybe solar radiation pressure was somehow pushing on its surface more effectively than expected. Each theory had problems. The nitrogen hypothesis required Oumuamua to have formed in conditions that exist only in the outer reaches of other star systems. The hydrogen ice theory faced the challenge that hydrogen ice shouldn't survive long in. Interstellar space thought the measurement uncertainties only added to the frustration. Oumuamua was small, distant, and moving fast. By the time astronomers realized how strange it was already racing away from the sun, becoming fainter with each passing day. We had maybe 2 months of useful data, explains Dr. Alan Fitzsimmons. Usually, we can observe asteroids and comets for years. With Oumuamua, we got a brief glimpse, and then it was gone. But that brief glimpse was enough to reveal something unprecedented. Here was an object that looked like an asteroid, moved like a comet, but behaved like neither dot when Professor Avi Loeb first suggested that Oumuamua might be artificial. The astronomical community didn't know quite how to react. This wasn't some fringe researcher making wild claims. This was the chair of Harvard's astronomy department, a scientist with over 700 peer-reviewed publications. Loeb's reasoning was elegantly simple and deeply unsettling. If you strip away all assumptions about what Oumuamua should be and just look at the data objectively, he argued the object's properties are remarkably consistent with a piece of artificial technology, specifically a light sail. Think about it, Loeb explains. We have an object with an extreme length to width ratio, showing acceleration that can't be explained by gravity alone, with no visible outgassing. If this were a piece of human technology, we'd immediately recognize it as a solar sail. The concept isn't science fiction. Light sails are real technology that we've already deployed in space. They work by using radiation pressure from starlight to provide propulsion, essentially surfing on light itself. Japan's Icarus mission successfully demonstrated solar sailing in 2010. The physics is well understood and proven, but here's what made Loeb's hypothesis so compelling. Oumuamua's properties perfectly match what you'd expect from a light sail, designed for interstellar travel. The extreme elongation. That's exactly what you'd want for an efficient sail. Maximum surface area to catch starlight. The mysterious acceleration. Radiation pressure acting on a thin, reflective surface. The lack of outgassing. No need for it if you're dealing with artificial technology. Loeb and his colleague Shmuel Bialy published their analysis in the Astrophysical journal Letters, showing that an artificial sail less than a millimeter thick could account for all of Oumuamua's observed properties. The scientific community's reaction was intense. Some colleagues praised Loeb for his willingness to think outside conventional frameworks, but many other astronomers pushed back hard. Some accused Loeb of seeking publicity or abandoning scientific rigor. Loeb found the reaction puzzling. The scientific method is supposed to be about following evidence wherever it leads, he says. But many scientists seem more interested in preserving conventional thinking than exploring unconventional possibilities. The irony wasn't lost on him. Here was a community dedicated to searching for life and intelligence in the universe. Yet when faced with potential evidence of alien technology, many astronomers reflexively rejected it. Loeb's hypothesis also raised fascinating questions about what alien technology might actually look like. If an advanced civilization wanted to explore the galaxy, they might well use lightweight probes propelled by starlight, exactly like Oumuamua appeared to be. Maybe the galaxy is filled with artificial objects, Loeb speculates, and we just haven't been looking for them properly. The implications were staggering. If Oumuamua was indeed artificial, it suggested that we live in a galaxy where intelligence is common enough that its products regularly pass through our solar system. Just as the astronomy community was grappling with Loeb's hypothesis, the universe provided what seemed like a perfect control experiment. In August 2019, Comet 2I Borisov was discovered, another interstellar visitor. This one behaved exactly as astronomers expected. Comet Borisov displayed all the classical features of a normal comet. It developed a beautiful coma and tail as it approached the sun. Its composition matched what we see in comets from our own solar system. Its nucleus appeared roughly spherical. Borisov was like meeting a familiar friend after encountering a mysterious stranger. Jokes. Dr. Fitzsimmons. It behaved exactly as our models predicted. Everything that Oumuamua wasn't, but instead of resolving the Oumuamua mystery, Borisov's conventional behavior made the first interstellar visitor seem even more anomalous. If interstellar objects typically behave like Borisov, then what was Oumuamua? The comparison forced astronomers to confront an uncomfortable statistical question. Dr. Amir Siraj from Harvard ran the numbers and reached a startling conclusion. Based on Oumuamua's discovery, objects like it should be incredibly common in interstellar space. Yet we've never seen anything else like it. The numbers don't add up, Siraj explains. Either Oumuamua represents an incredibly rare type of natural object, or it represents something else entirely. This statistical puzzle led some researchers to examine the broader context of anomalous astronomical discoveries. Throughout history, objects that initially seemed to defy explanation often turned out to be the first examples of entirely new categories of phenomena. Pulsars were first discovered in 1967. Their perfectly regular radio signals were so unusual that astronomers briefly considered whether they might be artificial beacons. They even nicknamed the first one LGM-1 for Little Green Men. The pattern was clear. When we encounter something genuinely unprecedented, our first instinct is to fit it into existing frameworks. Only when those frameworks fail do we begin to consider more radical possibilities. This limitation highlighted a broader problem in SETI research. Most SETI programs focus on detecting artificial signals from space, but what if alien technology looks nothing like our radio transmissions? What if it takes the form of physical objects that we might easily mistake for natural phenomena? Dr. Jason Wright from Penn State argues that we may need to expand our definition of what we're looking for. We've been searching for aliens by listening for their radio signals, Wright explains. But maybe we should also be looking for their artifacts. Current astronomical surveys are optimized to find and track objects, not to determine whether they're natural or artificial. We classify objects based on their orbits and brightness, not their detailed properties. Some researchers have calculated that if even 1 in a million star systems produces a technological civilization, and if each creates millions of interstellar probes, then there could be more artificial objects in the galaxy than natural ones. This perspective transforms how we think about Oumuamua. Instead of being an inexplicable anomaly, it might be our first glimpse of the true nature of the galaxy, a place where the products of intelligence are. Commonplace thought of all the mysteries surrounding Oumuamua. Perhaps none is more tantalizing than the question of its trajectory. When you strip away all the debates about composition and origin, one fundamental question remains. Was its path through our solar system coincidental, or was it chosen? Oumuamua's path was remarkably efficient. The object approached from the direction of Vega, swung around the sun at just 37 million kilometers, close enough to receive maximum acceleration, and then departed along a trajectory that gave it the most efficient escape from our solar system. If you were designing a probe to survey our solar system, you couldn't ask for a better trajectory. Admits Dr. Weiss, it gave the object a close look at the sun, passed near several planets, and provided maximum acceleration for the journey to the next star system. Mission planning experts who analyzed the trajectory found the path suspiciously well optimized. Computer simulations of random interstellar objects show that most would follow much less efficient paths. Oumuamua's path falls into a narrow range of trajectories that mission planners would consider optimal. The departure angle is equally intriguing. After its solar encounter, Oumuamua left along a trajectory aimed toward a region where other star systems cluster. Its current heading will take it toward the constellation of Pegasus, where it will encounter another stellar neighborhood in roughly 20,000 years. Could Oumuamua be following an interstellar highway, visiting multiple star systems in sequence? Dr. Loeb has calculated that an intelligently designed probe could visit dozens of star systems over millions of years by using gravitational slingshot maneuvers. The probe would use stars as stepping stones, gaining velocity from each encounter. It's the ultimate slow boat to anywhere, Loeb explains. But if you're a civilization thinking in geological timescales, it's an incredibly efficient way to explore the galaxy. The trajectory question also raises questions about timing. Oumuamua was the first interstellar object we ever detected, discovered just as our detection capabilities reached the necessary threshold. Some astronomers find this timing suspiciously convenient, but there's another possibility that few discuss publicly. What if the timing wasn't coincidental? What if Oumuamua's arrival was deliberately timed to coincide with our technological capability to detect it? Some researchers have even suggested that Oumuamua's unusual tumbling motion might have been intentional, a way to create distinctive light signatures that would distinguish it from natural objects. If you wanted to design an object that would capture astronomers' attention, you'd make it tumble in an unusual way, speculates Dr. Jacob Hack-Misra. You'd give it properties that clearly distinguished it from natural objects. A probe following an obviously artificial trajectory might serve as a calling card, a way of announcing presence without being overly intrusive. Civilizations that have achieved interstellar travel might approach newly technological species with caution, testing their readiness through indirect means. The trajectory evidence, while suggestive, isn't conclusive proof of artificial origin. But as our detection capabilities improve and we discover more interstellar visitors, the question will become increasingly important. Until then, we're left with a tantalizing possibility that the first interstellar object we ever detected might have been following a course plotted by intelligence. As I write this, Oumuamua is roughly 5 billion kilometers from Earth, racing away from our solar system at 26 kilometers per second. It's now fainter than the dimmest objects our most powerful telescopes can detect, carrying its secrets back into the darkness between stars. We had our chance. For a few precious months in late 2017 and early 2018, this mysterious visitor was close enough to study. We pointed every available telescope at it, analyzed its light, tracked its motion, and measured its properties with all the precision our technology could muster, but it wasn't enough. The data we collected raises more questions than it answers. We know Oumuamua was unlike anything we'd ever seen, extremely elongated, mysteriously accelerating, showing no signs of the outgassing that should accompany such acceleration. But we don't know what it was. This uncertainty reflects a fundamental challenge in studying interstellar visitors. Unlike objects in our own solar system, which we can observe repeatedly over years, interstellar objects are fleeting encounters. They appear from darkness, race through our solar system, and disappear back into the void. We get one chance. One brief window to gather evidence and draw conclusions. So where does this leave us with the central question? Was Oumuamua's path chosen? The honest answer is that we may never know for certain. The evidence is intriguing but not conclusive. The object's efficient trajectory, its unusual properties, and its apparent optimization for solar system exploration all hint at possible artificial origin. But these same features might also be explained by natural processes we don't yet understand. Consider what Oumuamua has taught us about our assumptions. Before its discovery, most astronomers assumed that interstellar objects would be essentially similar to our own. Comets and asteroids, perhaps with slightly different compositions, but fundamentally familiar. Oumuamua shattered those assumptions. It showed us that the galaxy might be filled with objects unlike anything in our cosmic neighborhood. More provocatively, it raised the possibility that some of what we observe in space might not be natural at all. This shift in perspective has already begun to influence how astronomers approach new discoveries. Survey programs are now more alert to unusual objects that might not fit conventional categories. Researchers are developing new methods to distinguish between natural and artificial signatures. Looking forward, we're entering a golden age of interstellar object detection. New survey telescopes will discover dozens or even hundreds of interstellar visitors over the next decade. Each new object will be an opportunity to test our theories about single quotes Oumuamua if future interstellar objects all behave like conventional comets and asteroids. It will suggest that Oumuamua was either extremely rare or possibly artificial. If we discover more objects with similar anomalous properties, it will indicate that our understanding needs major revision. Either outcome will advance our knowledge significantly. But perhaps the most important lesson from Oumuamua is about intellectual humility. The universe is under no obligation to conform to our expectations. When we encounter something that challenges our understanding, our first instinct should be curiosity, not dismissal. Avi, Loeb's willingness to seriously consider artificial origins, despite professional criticism, exemplifies the intellectual courage that drives scientific progress. Whether or not he's correct about Oumuamua specifically, his approach reminds us that extraordinary possibilities require extraordinary investigation. The debate has also revealed tensions. within the scientific community about balancing skepticism with openness. While healthy skepticism prevents us from accepting extraordinary claims without evidence, excessive skepticism can blind us to extraordinary realities. Finding the right balance is crucial. As we enter an era where detecting artificial objects in space becomes increasingly plausible, we now know that thousands of exoplanets exist, many potentially habitable. We understand that the basic chemistry of life is common throughout the universe. In this context, the idea that we might encounter artifacts from other civilizations is not far-fetched. It's almost inevitable. The question is whether we'll recognize them when we see them. Oumuamua may have been our first test of this recognition capability. Whether we passed or failed remains an open question. What's certain is that our cosmic neighborhood is far stranger than we imagined. Every object that passes through our solar system carries information about other star systems, other epochs of cosmic history, and possibly other forms of intelligence. Oumuamua forced us to confront fundamental questions about the nature of reality. It challenged us to expand our conception of what's possible and to remain open to discoveries that might reshape our understanding of everything. That the answer to whether its path was chosen may remain forever beyond our reach. But the questions it raised will continue to guide our exploration of the cosmos for generations to come. Somewhere out there, beyond the edge of our solar system, Oumuamua continues its journey through the galaxy. It carries with it the mystery of its origin, the secret of its true nature, and perhaps the key to understanding whether we are alone in the universe. We may never solve the riddle of Oumuamua, but in wrestling with its mysteries, we've already begun to answer a deeper question about ourselves, whether we're ready to recognize intelligence when it comes calling from the stars.